Hi, I'm Geraldo, a PhD student at the Safari Research Group, and today I'm going to talk about our work titled Polynesia, Enabling High Performance and Energy Efficiency Hybrid Transactional Analytical Databases with Hardware Software Co-Design. This work was led by Amirali Burman, who is now at Google. Traditionally, database management systems uses two separate systems to perform transactions and analytics over some data. This creates some issue since data migration between transactional and analytical database management systems can take hours to days depending on the volume of data. To solve this issue and support real-time data analysis, prior works have proposed a hybrid transactional analytical processing system, or HTAP. As the name indicates, such a system has the ability to perform both transaction and analytics concurrently. In order to allow for real-time data analysis, a HTAP system should provide three key properties. First, workload-specific optimizations. Second, data freshness and consistency guarantees. And third, performance isolations to transactional and analytical workloads. However, achieving all of the three desired HTAP properties can be very challenging. We extensively analyzed state-of-the-art HTAP systems, and we identified three major limitations of state-of-the-art systems. The first one being that they cannot meet all of the three desired HTAP properties, failing to provide high data freshness and consistency, performance isolations, and workload-specific optimizations. Second, data freshness and consistency mechanisms suffer from data movement overhead and are data-intensive, leading to a reduction in transactional and analytical throughput. Third, the system fails to provide performance isolation due to high contention at main memory. Based on that, our goal in this work is to take advantage of custom algorithms and hardware to address such limitations of HTAP system. The key idea behind our mechanism is to partition the computing resources into two types of isolated processing islands, one island dedicated to transaction and another island dedicated for analytical workloads. By isolating transactional workloads using transactional islands from analytical workloads using analytical islands, we can apply workload-specific optimizations to each island, avoid high research contention, and design efficient data freshness and consistency mechanisms while mitigating data movement costs. Polynesia leverages processing memory, or PIM, techniques to reduce the data movement caused by data freshness and consistency mechanisms. Processing memory can mitigate data movement overheads by adding computing units near or inside memory devices. Based on that, we propose Polynesia, a hardware software co-design HTAP system. Polynesia includes tailored transactional and analytical islands that include a replica of the data, optimized execution engines, and specialized hardware resources. Next, I'm going to briefly describe the main components of Polynesia. First, the transactional island includes an execution engine tailored for transactions and a replica of the data. The transactional island is designed to sustain high transactional update rates. Thus, it uses conventional multi-core CPU systems with a deep cache hierarchy, since transactional workloads benefit from such CPU organization. Second, the analytical island is implemented inside the logic layer of a 3D stack memory. The 3D stack memory connects layer of DRAM banks with a layer of logic using high throughput through silicon vias, or TSVs. Vertical partitions of the 3D stack memory is called a vault. We place hardware resources inside each vault of the 3D stack memory, including an execution engine tailored for analytics, a replica of the data. The analytical island is designed to provide higher read throughput. Thus, the analytical island leverages simpler process memory cores that can mitigate data movement caused by data analytics. We co-design algorithms and hardware units that can efficiently maintain data consistency and data freshness in your analytical island. We invite you to check our paper for a comprehensive discussion of the Polynesia design. We extensively evaluate Polynesia, and we see that it can achieve 91.6% of the transactional throughput of our ideal system by employing custom process memory logic for data freshness and consistency, while reducing the cost of data movement and research contention at main memory. Polynesia also improves the analytical throughput by 63.8% over optimized multiple instance systems by eliminating data movement and again using custom logic for update propagation and consistency. Overall, Polynesia achieves all the three desired HTAP properties from a HTAP system and has a higher transactional and analytical throughput over prior works. Next, I'm going to conclude this talk. Many applications today are required to perform real-time data analysis, meaning that they need to execute data analysis with the most recent version of the data using an HTAP system. This HTAP system should provide three key properties: data freshness and consistency, workload-specific optimizations, and performance isolation. We extensively analyzed the state-of-the-art HTAP systems, and we observed that they failed to meet all of the 3 desired HTAP properties. Therefore, a key idea to solve this issue is to divide the HTAP system in processing islands, one for transactional and another for analytical workloads. Each island has a set of optimized hardware resources and algorithms. By enabling processing islands, we can perform workload-specific optimizations to transactional and analytical workloads while providing performance isolations. We leverage our key idea to implement Polynesia, a novel hardware software co-designed HTAP systems that implement custom algorithms and hardware to reduce the cost of maintaining data freshness and consistency in the HTAP system, and exploit processing memory to alleviate data movement costs caused by analytical workloads. We extensively evaluate Polynesia against 3 state-of-the-art HTAP systems, and we observe that it can increase its transactional analytical throughput by 1.7 times and 3.7 times on average, and reduces energy consumption by 48%. Thanks a lot for listening, and you can check our paper in the QR code below.